Looking at elements of group 4 below carbon: silicon, germanium, tin, and lead. Properties of elements themselves change a lot from silicon to lead. Silicon is typical non-metal with very high melting point. To a lesser extent, the same can be told about germanium. Tin and lead both have low melting points. Silicon never forms ions. Actually, germanium never forms 4+ ions. We can talk about ions of tin and lead in oxidation number +2. Ions in oxidation number +4 exist only in crystalline form and never in solution. All of them have approximately the same electronegativity, around 2, much lower than carbon. Sources of this element: silicon is the most abundant element in Earth's crust, forms plenty of minerals. Of pure silicon mineral, most important is quartz itself, which is silicon dioxide. Forms beautiful, sometimes enormous crystals, different form. Impurities can color it in beautiful colors, making it semi-precious stones. Despite the formula SiO2, there are never SiO2 molecules. The structure is made of SiO4 tetrahedral groups that are glued together. So total number of oxygen is twice larger than total number of silicon atoms in this form. Actually, quartz is chiral compound, is optical activity. Production: germanium is mainly isolated from zinc ores, where it is an admixture. Tin has own mineral, most common is cassiterite, tin oxide. Known by ancients, was mined for thousands of years. Most common mineral that is lead ore is galena, which is lead sulfide. There is a town in Illinois named Galena, known for lead sulfide mining. To make silicon element, SiO2, silicon dioxide, is reduced to silicon by carbon. This synthesis leads to large admixture of silicon carbide. So silicon needs to be purified. It can be treated with gaseous hydrogen chloride to make SiHCO3 gas, which later can be decomposed in presence of large amount of hydrogen, making silicon of much higher purity. Germanium oxide can be reduced to germanium with carbon monoxide. Tin dioxide can be reduced to tin with carbon. Because with lead we are starting with sulfide, we need to remove it, and usual procedure can be written as roasting, so PbS plus O2 making Pb plus SO2. It does not describe the whole picture. In fact, lead sulfide reacts with oxygen to make lead monoxide and SO2, and then lead oxide in turn is reduced by carbon to make metal lead and carbon monoxide. Roasting reflects the fact that carbon-containing fuel is used to roast lead ore. Silicon for electronic uses need to be purified, and the most common process is zone refining or Czochralski process. Process depends on fact that impurities are more soluble in liquid phase than in solid phase. A rod of silicon is moved through high temperature electric coil that partially melts the silicon. As part of the rod moves beyond the coil, silicon resolidifies. During the solidification process, impurities diffuse into the portion of the rod that is still molten. After entire rod has passed through the coil, impurity-rich portion can be removed. Procedure can be repeated until desired level of purity is obtained, and this is just a view of crystal of silicon after purification. Silicon and germanium has the same structure as diamond. It's cubic with tetrahedral atom surrounded by the same tetrahedral atoms. The same structure is for cold gray tin. Germanium forms crystals purified again by Czochralski process that look very similar to silicon. Tin can have two major forms. One, so-called white tin, is more or less common metal, widely used for different solders, toxic lead tin solder, and non-toxic tin silver copper solder, which are very common. Most of tin, and its enormous amount, is used for solder making. Some of them is used for making brasses, bronzes, and for covering the steel surface tin plate. An interesting transition occurs with tin at around 13 degrees Celsius when metal becomes plugged, so-called tin pest or tin plug. Metal becomes non-metal. Tin comes to be diamond-like, non-metallic, similar to silicon and germanium. These processes can destroy objects made of tin. Fortunately, it's relatively slow, so at 13 Celsius you see nothing. Only if you freeze to very low temperature, the process becomes really quick. Now, lead is usual metal, having face-centered cubic lattice, nothing special.